In computer science and computer programming, a data type or simply type is a classification identifying one of various types of data, such as real, integer or Boolean, that determines the possible values for that type, the operations that can be done on values of that type, the meaning of the data, and the way values of that type can be stored. Overview. Data types are used within type systems, which offer various ways of defining, implementing and using them. Different type systems ensure varying degrees of type safety. Almost all programming languages explicitly include the notion of data type, though different languages may use different terminology. Common data types include integers, booleans, characters, floating point numbers, alphanumeric strings. For example, in the Java programming language, the int type represents the set of 32-bit integers ranging in value from -2,147,483,648 to 2,147,483,647, as well as the operations that can be performed on integers, such as addition, subtraction, and multiplication. Colors, on the other hand, are represented by 3 bytes denoting the amounts each of red, green, and blue, and 1 string representing that color's name. Allowable operations include addition and subtraction, but not multiplication. Most programming languages also allow the programmer to define additional data types, usually by combining multiple elements of other types and defining the valid operations of the new data type. For example, a programmer might create a new data type named complex number, that would include real and imaginary parts. A data type also represents a constraint placed upon the interpretation of data in a type system, describing representation, interpretation and structure of values or objects stored in computer memory. The type system uses data type information to check correctness of computer programs that access or manipulate the data. Most data types in statistics have comparable types in computer programming, and vice versa, as shown in the following table. Definition of a type. Identified 5 definitions of a type that were used, sometimes implicitly, in the literature. Syntactic. A type is a purely syntactic label associated with a variable when it is declared. Such definitions of type do not give any semantic meaning to types. Representation. A type is defined in terms of its composition of more primitive types, often machine types. Representation and behavior. A type is defined as its representation and a set of operators manipulating these representations. Value space. A type is a set of possible values which a variable can possess. Such definitions make it possible to speak about unions or Cartesian products of types. Value space and behavior. A type is a set of values which a variable can possess and a set of functions that one can apply to these values. The definition in terms of a representation was often done in imperative languages such as ALGOL and Pascal, while the definition in terms of a value space and behavior was used in higher-level languages such as Simula and CLU. Classes of data types. Primitive data types. Machine data types. All data in computers based on digital electronics is represented as bits on the lowest level. The smallest addressable unit of data is usually a group of bits called a byte. The unit processed by machine code instructions is called a word. Most instructions interpret the word as a binary number, such that a 32-bit word can represent unsigned integer values from 0 to or signed integer values from 2, because of 2's complement. The machine language in machine doesn't need to distinguish between these unsigned and signed data types for the most part. There is a specific set of arithmetic instructions that use a different interpretation of the bits in word as a floating point number. Machine data types need to be exposed or made available in systems or low-level programming languages, allowing fine-grained control over hardware. The C programming language, for instance, supplies integer types of various widths, such as short and long. If a corresponding native type does not exist on the target platform, the compiler will break them down into code using types that do exist. For instance, if a 32-bit integer is requested on a 16-bit platform, the compiler will tacitly treat it as an array of two 16-bit integers. Several languages allow binary and hexadecimal literals, for convenient manipulation of machine data. In higher-level programming, machine data types are often hidden or abstracted as an implementation detail that would render code less portable if exposed. For instance, a generic numeric type might be supplied instead of integers of some specific bit width. Boolean type. The Boolean type represents the values true and false. Although only two values are possible, they are rarely implemented as a single binary digit for efficiency reasons. Many programming languages do not have an explicit Boolean type, instead interpreting 0 as false and other values as true. Numeric types such as the integer data types, or whole numbers, may be subtyped according to their ability to contain negative values. May also have a small number of predefined subtypes, or allow users to freely define subranges such as 1, 12. Floating point data types, sometimes misleadingly called rails, contain fractional values. They usually have predefined limits on both their maximum values and their precision. These are often represented as decimal numbers. Fixed point data types are convenient for representing monetary values. They are often implemented internally as integers, leading to predefined limits. Big num or arbitrary precision numeric types lack predefined limits. They are not primitive types, and are used sparingly for efficiency reasons. Composite types. Composite types are derived from more than one primitive type. This can be done in a number of ways. The ways they're combined are called data structures. Composing a primitive type into a compound type generally results in a new type, e.g., array of integer is a different type to integer. An array stores a number of elements of the same type in a specific order. They are accessed randomly using an integer to specify which element is required. Arrays may be fixed length or expandable. A list is similar to an array, but its contents are strung together by a series of references to the next element. Records are among the simplest data structures. A record is a value that contains other values, typically in fixed number and sequence and typically indexed by names. The elements of records are usually called fields or members. Union. A union type definition will specify which of a number of permitted primitive types may be stored in its instances, e.g., float or long integer. Contrast with a record, which could be defined to contain a float and an integer, whereas, in a union, there is only one value at a time. A tagged union contains an additional field indicating its current type, for enhanced type safety. A set is an abstract data structure that can store certain values, without any particular order, and no repeated values. Values themselves are not retrieved from sets. Rather, one tests a value for membership to obtain a Boolean in, or not in. An object contains a number of data fields, like a record, and also a number of subroutines for accessing or modifying them, called methods. In contrast, data structures not containing code, like those above, are called plain old data structures. Many others are possible, but they tend to be further variations and compounds of the above. Enumerations. The enumerated type. This has values which are different from each other, and which can be compared and assigned, but which do not necessarily have any particular concrete representation in the computer's memory. Compilers and interpreters can represent them arbitrarily. For example, the 4 suits in a deck of playing cards may be 4 enumerators named club, diamond, heart, spade, belonging to an enumerated type named suit. If a variable v is declared having suit as its data type, one can assign any of those 4 values to it. Some implementations allow programmers to assign integer values to the enumeration values, or even treat them as type equivalent to integers. String and text types such as alphanumeric character, a letter of the alphabet, digit, blank space, punctuation mark, etc. Alphanumeric strings, a sequence of characters. They are typically used to represent words and text. Character and string types can store sequences of characters from a character set such as ASCII. Since most character sets include the digits, it is possible to have a numeric string, such as 1234. However, many languages would still treat these as belonging to a different type to the numeric value 1234. Character and string types can have different subtypes according to the required character width. The original 7-bit wide ASCII was found to be limited, and superseded by 8 and 16-bit sets, which can encode a wide variety of non-Latin alphabets and other symbols. Strings may be either stretched to fit or of fixed size, even in the same programming language. They may also be subtyped by their maximum size. Note: strings are not primitive in all languages. For instance, C. They may be composed from arrays of characters. Other types can be based on, or derived from, the basic types explained above. In some languages, such as C, functions have a type derived from the type of their return value. Pointers and references. The main non-composite derived type is the pointer, a data type whose value refers directly to another value stored elsewhere in the computer memory using its address. It is a primitive kind of reference. Pointers are often stored in a format similar to an integer. However, attempting to dereference or look up a pointer whose value was never a valid memory address would cause a program to crash. To ameliorate this potential problem, pointers are considered a separate type to the type of data they point to, even if the underlying representation is the same. Function types. Abstract data types. Any type that does not specify an implementation is an abstract data type. For instance, a stack can be implemented as an array, or as a linked list. Abstract types can be handled by code that does not know or care what underlying types are contained in them. Programming that is agnostic about concrete data types is called generic programming. Arrays and records can also contain underlying types, but are considered concrete because they specify how their contents or elements are laid out in memory. Examples include, a queue is a first-in first-out list. Variations are dec and priority queue. A set can store certain values, without any particular order, and with no repeated values. A stack is a last-in, first-out data structure. A tree is a hierarchical structure. A graph, a hash, dictionary, map or associative array is a more flexible variation on a record, in which name-value pairs can be added and deleted freely. A smart pointer is the abstract counterpart to a pointer. Both are kinds of references. Utility types. For convenience, high-level languages may supply ready-made, real-world data types, for instance times, dates and monetary values and memory, even where the language allows them to be built from primitive types. Type systems. A type system associates types with each computed value. By examining the flow of these values, a type system attempts to prove that no type errors can occur. The type system in question determines what constitutes a type error, but a type system generally seeks to guarantee that operations expecting a certain kind of value are not used with values for which that operation does not make sense. A compiler may use the static type of a value to optimize the storage it needs and the choice of algorithms for operations on the value. In many C compilers, the float data type, for example, is represented in 32 bits. In accord with the IEEE specification for single precision floating point numbers, they will thus use floating point-specific microprocessor operations on those values. The depth of type constraints and the manner of their evaluation affect the typing of the language. A programming language may further associate an operation with varying concrete algorithms on each type in the case of type polymorphism. Type theory is the study of type systems. Although the concrete type systems of programming languages originate from practical issues of computer architecture, compiler implementation, and language design, type systems may be variously static or dynamic, strong or weak typing, and so forth.